Okay, let's do a 3 by 3 example with one of these defective eigenvalues. Remember, defective eigenvalue means that the algebraic multiplicity, the number of times the factor appears in the factorization, is, well, it's different from the geometric multiplicity, the maximum number of linearly independent eigenvectors that you can find with that eigenvalue. Okay, so I'm going to pull this straight from the textbook, and I'm going to skip some steps. And I suggest that if any of this gives you grief, that you fill in the steps that I skip. But we're going to look at the matrix P, which is a 3 by 3 matrix. It's going to be 1, 3, 3, 1, 1, 0, and negative 1, negative 1, negative 1, 1, 2. Very important I don't get this wrong. Okay. Okay, so we're going to begin by finding the characteristic polynomial. Characteristic polynomial. So I'm just going to do the linear algebra side of things. I'm going to find the eigenvalues, eigenvectors, and all of that business first, and then we'll analyze what that information that we get tells us about solutions to x prime equals px. That's our ultimate goal after all. The characteristic polynomial is going to be the determinant of the following 3 by 3. 1 minus lambda, 3, 3, 1, 1 minus lambda, 0, negative 1, 1, 2 minus lambda. And there's not so much profit to be had. Maybe what I'll do is do a cofactor expansion along, I don't know, column 3? Let's do it. Column 3. Because we haven't done that typically. All right. Now, I need to be careful and wary of signs, okay? Because this entry right here is in the 1, 3, no. Yeah, no, I'm right. 1, 3 position. And so it's going to get a positive sign. So this is going to be equal to 3 times the determinant of the 2 by 2 that I get by deleting row 1 and column 3. That 3 by 3 right there. And if I write it out, what I get is 1, because 1 times 1 is 1, minus what I get by multiplying negative 1 by 1 minus lambda. But that's plus 1 minus lambda. I put 1 minus lambda in parentheses because I got good hygiene that way. I like my parentheses, okay? So that's the first term. The second term I'm going to get by doing this cofactor expansion along this term now. That term's in the 3 position. 3 plus 3 is even. Negative 1 to an even is positive. So we're going to get a plus, therefore, 2 minus lambda. Again, parentheses, not optional there. Times the determinant of the 2 by 2 that I get by deleting the third column and third row. That 2 by 2 right there. So I get 1 minus lambda squared minus 3. Okay. Well, I don't know what happens now. Let's see. Let's see what we can see here. So if I distribute the 3, I get 3 plus 3 times 1 minus lambda. I'm being cautious here because I'm looking on the lookout for any moves that I can make. 2 minus lambda times, well, if I guess I should maybe expand that out. Let's see. I'm just not sure. So if I expand that out, I get 1 minus 2 lambda plus lambda squared minus 3. I think this is the one I really should be expanding out. That gives me 3 plus 3 minus 3 lambda. Okay. Oh, okay, something nice does happen there. Okay, plus, and let me describe what that is. 2 minus lambda times 1 minus, and I'll clean this up. This looks like lambda squared minus 2 lambda, and I believe that's a minus 2. Okay, so what's the nice thing that happens here? This becomes 6 minus 3 lambda. Do you agree? You can't answer. And the reason I like that is because I notice with my my eyeballs that this is 3 times this. And so what I can do is rewrite, yeah, sorry. I probably shouldn't have distributed up here. That was a little redundant. But in any case, this is 3 times this. That's what I'm seeing with my eyeballs. So I can rewrite this as 3 times 2 minus lambda. Now, do you see why that's cool? It's because now I see that 2 minus lambda is a factor of both of these terms, so I can factor it out. And be left with 3 plus lambda squared minus 2 lambda minus 2. 3 minus 2 is 1, so this looks like 2 minus lambda times lambda squared minus 2 lambda plus 1. And I believe that's a perfect square. Do you agree? You can't answer. But yeah, it's true. So what we see here is we have 2 eigenvalues. Lambda equal to 2 and lambda equal to 1. Lambda equal to 2 is an eigenvalue with algebraic multiplicity 1. Lambda equal to 1, however, is an eigenvalue with algebraic multiplicity 2. Lambda equals 1, though, is an eigenvalue with algebraic multiplicity 2. Why 1 and 2? Because that's the number of times their respective factors appear in the factorization. Okay. Okay. Now, you can check. I'm encouraging you, imploring you to do this, okay? You can check that for lambda equal to 2, we have an eigenvector. And the eigenvector is 3, 3, negative 2. I'm not going to do this myself because I don't want to. And that the corresponding eigenvalue is 2. Okay? This is what's called an eigenpair. And you can also check another eigenpair is given by 0, 1, negative 1. This is an eigenvector with eigenvalue 1. Unfortunately, you can also check this, and maybe I will check this. In fact, this eigenvector is the only, in some sense, eigenvector. Every other eigenvector is a scalar multiple of this one. You know what? I shouldn't check that. Sorry, you shouldn't check that. I should check that for you, because this is really where the heart of the defectiveness of lambda equal to 1 comes in. So let's check that claim that I just made, okay? So this is an eigenpair. I won't check that. That's a standard calculation, and you should be pros at this. But I will study or analyze lambda equal to 1 because I love you. So lambda equal to 1. Let's see that one together. So let's remind ourselves of what P is. I'm going to draw it down from here. Uh-oh. Let me do this better. There's my, I'm just going to put it right there, just as a reminder, okay? Then what we want to solve here, we want to solve this system. So P1, so 1 minus 1 is 0, 3, 3, 0, no. Ooh, don't make mistakes by going too fast like I do. We want to solve this system. Equals 0, sorry, times v equals the 0 vector, 0, 0, 0. Because I'm hunting for eigenvectors, okay? Now, one thing I notice is that I can add row 2 to row 3. Maybe I should make an augmented matrix, shouldn't I? I can add row 2 to row 3. And what I get when I do that is 0, 1, 1, 0. And now do you see that row 3 is a multiple of row 1? So I can kill either one. And I can also multiply row 1 by 1/3. I like doing that because I like 1s more than 3s. That's not even true. I like 3s. It's one of my favorite numbers. What's your favorite number? Ew. My favorite number is 4. And 3 and 4. Sorry. I like 3 and 4. You know why I like 4? It's 2 plus 2. So anyway, moving on. So what this tells me is that V1 must be 0. And, sorry. Let me go in order here. This tells me two things. From the first equation, that V2 plus V3 must be 0. Cool. And that V1 must be 0. So I can write down an eigenvector relatively easily. I just need that V1 is 0. V1 is 0, and that V2 and V3 be negatives of each other. So I might as well take V2 to be 1, and therefore V3 is negative 1. So this is an eigenvector, and my associated lambda is 1. And I believe this is exactly what I told you earlier. This is an eigenpair. All right. But I can't find additional eigenpairs that are linearly independent from this 0, 1, negative 1. I can't find another eigenvector because the constraints that I know must be imposed by any eigenvector are these two. Okay? Those two constraints, how can I say it? I want you to think like an engineer maybe. Okay? Think about it in terms of degrees of freedom. Before you have any constraints, there are 3 degrees of freedom on V. 0, here's 1, 2, 3, because we had 3 entries. So we had 3 degrees of freedom. But then we have these 2 constraints that are arising. And because we have 2 constraints, that leaves 1 degree of freedom. That 1 degree of freedom is met by this vector, but every other vector is simply going to be a scalar multiple of this one. That's what it means to have 1 degree of freedom. Okay? So this is it for eigenvectors. We're done. So what we need to do is find what's called a generalized eigenvector. Okay? So going way back, we remember the sort of generalized eigenvector story. What we want to solve is P minus lambda times the identity. I'm looking right here, sorry. P minus lambda times the identity times some vector V is equal to our eigenvector. V1, remember, was our eigenvector. Okay? So we want to solve P minus lambda times the identity times V is equal to our eigenvector. In this case, that's 0, 1, negative 1. This V here is not the same as that V there. Okay, I'm resetting on V. Maybe I'll call it W. Should I do that? Maybe I should do that. Generalized eigenvector W, which we'll call W. W, I'll sit right here. I want to solve this equation. What was lambda again? It's 1. Okay, so I'm going to shove in lambda equal to 1 again. And what I get is the augmented matrix then. It's just this one, 0, 3, 3, 1, 0, 0, negative 1, 1, 1. But now I'm going to augment 0, 1, negative 1. And I want to solve this system now. Okay? Well, let's do it. Let's do row reduction. So I'm going to multiply row 1 by 1/3. I'm going to leave row 2 intact, and I'm going to add row 2 to row 3 because I want to kill this negative 1. I like killing negative 1s. 0, 1, 1, 0. And now I notice that row 1 and row 3 are identical. So I can kill row 3. I like killing rows. Oh, shoot. I messed. Oh, my God. That would have been fatal. This 0 is a 1. Okay. So what is this system telling me now? This system tells me that v2 plus v3, first row tells me v2 plus v3 is 0. Okay. Second equation is telling me v1 must be equal to 1. And the third row is totally and completely vacuous. So v1 must be 1. v2 and v3 can be anything which add to 0. So why not take just v2 and v3 to be 0? Oh, and by the way, I shouldn't have used v's. Because, sorry, I'm used to using v's when in my eigenvector calculations. But really, I should be using w's, right? I'm going to think of w as being the 3 tall vectors, w1, w2, w3. So really what I'm saying here is that w2 plus w3 is 0, and w1 is 1. Okay, so my generalized eigenvector is going to be, I'm going to take it to be 1, 0, 0, because why not? Okay. So then look at all the data that I've got here, crucially. I've got these two eigenpairs. Okay. And now I've got my generalized eigenvector. Each of those circled pieces is going to give me a solution to the differential equation x prime equals px. And so I can mash them into a gigantic superposition to get what I want. Now I need to be a little careful with the generalized eigenvector. So let's figure that part out. So first thing, let's write down the general solution now to the system x prime equals px. What is p again? P is this guy. Right there. That guy. I don't know what I'm doing. I'm sorry. I've lost my mind. So let's write it all out. So we get that x is equal to c1. Now I'm going to look at my first eigenpair. Here it is. 3, 3, negative 2, comma 2. So that's going to be c1 times that v times e to the lambda t. So that's 3, 3, negative 2 times e to the 2t. Okay, cool. Next, I'm going to use my second eigenpair. Second eigenpair is sitting right here. See it? That tells me I have, again, same format, same ansatz. I have 0, 1, negative 1 times e to the 1t, which is just e to the t. Okay? And then finally, I have the solution arising from my generalized eigenvector. That's going to be my, oh, and I should put parentheses. It's going to be parentheses. It's going to be my generalized eigenvector. That's 1, 0, 0. Plus t times the eigenvector, which is 0, 1, negative 1. Times e to the t. There it is. Very potentially confusing this, but you got to go back to the story that we've got written here. All right? Right? P, look here. Look at this this guy here, right? No, don't look at that guy there. Look at the ansatz. That's where you really want to look. My bad. Look at the ansatz. Generalized eigenvector plus eigenvector times t times e to the lambda t. Okay. All right. That's it. That's all I need to say, I hope. Hopefully you'll have practice doing this in the not so distant future. Okay, so long.